relationship between period and frequency? The relationship between period and frequency is...
Period is the measure of how many fulls whatever you're measuring happen in a certain amount of time. And frequency is how far it goes in 1 second.
Half of what you said is correct. So, and you define them. So frequency is how many cycles you get in per second, whether it's a full cycle, whether it's a tenth of a cycle. Frequency is cycles per second. What's period? What's the mathematical? Well, if you can't answer that, what's the mathematical relationship between the two? They are inverses. Yeah. So frequency equals 1 over period. Period equals 1 over frequency. And period is the amount of time it takes for a full cycle of motion, where frequency is the number of cycles that can be accomplished in a unit of time. Okay, so that's where we left our heroes. Now we want to look at something, and I did get your labs graded. I don't know if I hit the return button on Classroom or not, but this was something that you basically looked at in your lab. You attempted to examine what affected period. Does the mass of the bob affect the period? Does the amplitude, the amount of deviation from equilibrium, affect period? Does the length of the pendulum affect period? What did you find? Did mass affect period? Mm-mm. Did the amplitude affect period? Not really. Did length affect period? Yeah. Length is the only one of these factors that really affects period. That is what controls period. The only thing that affects period and frequency is the length of the pendulum. Mass doesn't, which seems weird. It seems like it should. Why does it seem like it should? Let me see. What's the restoring force in a pendulum? What's this restoring force in a pendulum? FGX, which means mass gravity sine. I have to think that one through. It always seems intuitively to me like mass should, and yet it does not. There is a factor in that FGX calculation that does, however. Free fall acceleration. So the length of the pendulum and G are what affect frequency, which means if you have a 1 meter pendulum on Earth and a 1 meter pendulum on the moon, will they have different frequencies? Yes. And, that's one of the classic kinds of, stupid physics textbook questions, chapter 47. You have constructed a 1 meter pendulum on an unknown planet. What is the free fall acceleration on this planet? Because that's how you'd figure it out. Actually, it wouldn't be a bad way to figure it out, come to think of it. It would be easier to measure than how fast something accelerated from rest. So, might not be bad. Okay. Maybe we'll do one like that, just for grins and giggles. This takes us to the 4B problems and how to compute period. So, as much of a believer as I am in deriving everything from scratch, I honestly have never found the derivation for this. T, which is period, and let me rewrite that so it's clearer, is equal to 2 times pi times the square root of the length of the pendulum over free fall, over gravity. And obviously here we use G with no negative because that is under a radical sign. It's we're taking the square root of that fraction. So did I just write 2? I did. T. Okay, so let's do the 4B sample problem on page 448. You want to talk about ridiculous physics problems setups. We do get some rather ridiculous physics problem setups. You have been apparently locked in a tower, held prisoner against your own will. You need to know the height of the tower, but darkness obscures the ceiling. This is like the pit and the pendulum. You note that a pendulum extending from the ceiling almost touches the floor and its period is 12 seconds. How tall is the tower? Do love these kind of ridiculous problems. So what we know is that t is equal to 2 pi square root of L over G. And we are solving for the length of the pendulum. So to rearrange this, we take t divided by 2 pi equals the square root of L over G. T over 2 pi squared equals L over G, which means that T over 2 pi quantity squared times G equals L. So now we have a rearrangement into which we can plug our variables. T equals 12 seconds, G 9.81 meters per second squared. You should have a raw answer of 35.782589, blah, 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 blah. Some of you are still clicking, that's fine. Obviously, if you don't use your pi button, you get a different raw value. How many sig figs do we get out of this? 2. So we get 36 meters. Now, let's do a quick dimensional analysis on this, because this is a complicated enough rearrangement, and it's got a couple of things that tend to trip people up, which is a radical, and it's got a fraction. And anytime we have both of those things, it's an easy way to trip yourself up. So, if we do the dimensional analysis on this. I'm going to copy that over. Did everybody get the raw answer? Okay, we'll look at what you're doing. Also lots of places for calculator entry error on this. So let's do the dimensional analysis. So period is given in what? Seconds. So we have seconds. 2 pi has no units. So this is unitless. So we just have seconds over 1. That quantity squared times gravity. Gravity is given in, acceleration due to gravity is given in what? Meters per second squared. We're looking for length, which should be, if we're doing things right, in meters. So we have seconds squared times meters per second squared equals meters. Is that true? Yep. Good. Meters equals meters. Okay, all of the problems, page 449, and I'll give you a couple minutes. Actually, we don't have all that long, huh? Oh, no, we do. I'll give you a couple minutes to work on these and kind of check in with people who are having issues, and then we'll move on to 4C. We said in a pendulum, a mass on a string or a cable, the length of the period was controlled by what? I just gave it away. Length of the string. What factor do you think is most important in controlling the period in a mass spring system? Spring constant's one of them, mass. So the mass and the spring constant are the two things that control the period there. And it's pretty intuitive. If we put a heavier mass or a lighter mass on this thing, the period's going to change. If we replace this with a stiffer or looser spring, the period's going to change. I mean, you can exhibit this pretty, I think this one's it's a lot more intuitive than the pendulum, because it seems like the mass should be playing a factor in the pendulum, but it's not. So that gets us, come on, you can do it, little iPad. There we go. That gets us here. The mass is the single largest controlling factor, so obviously spring constant can't be ignored. And if you look at the, well, we're going to look at the equation in a second for period. It's going to look awfully familiar to you. But in essence, more mass does give you more inertia, and it gives you more momentum. Okay? So you tend to have more restoring force because there is more movement away from equilibrium. And then there's more momentum to return you past equilibrium, which means more gravitational force on that mass. Okay. And the other factor, and you addressed this immediately, is the spring constant. So a looser spring is going to have a longer cycle of motion. A tighter spring will have a much shorter cycle of motion. If you have ever ridden in a large truck that did not have a load in it, so 1-ton pickup truck with nothing in the back, ride's pretty hard because the large springs that are designed to support a heavy load in the back have a relatively short period of motion. That means you get jarring, hard ride. If you have a looser spring, you tend to get a gentler, softer ride. For a number of years after college, I drove a 1988 Chevy Celebrity. It was my grandma's car. When she died, I got it. And it was designed to appeal to little old ladies. I mean, my grandma was the target audience for this vehicle. And though it was a little 4-cylinder, it had these super soft, super loose suspension springs. So it steered through corners like a boat because it had very soft springs. They tended to have a nice, long period to their vibration, which made a very soft ride. Okay. Now we get to go to the math. This is going to look familiar. T equals 2 pi times the square root of m over k. What does that look an awful lot like? T equals 2 pi square root of L over G. And in this case, the length is replaced by mass. Gravitational free fall is replaced by the spring constant. So we'll go straight. And the amplitude, if we distend this spring manually, that's not going to change the period. Whoops. Well, I knew that would happen sooner or later. Boing. I'll find it in a little bit. The period is independent of the amplitude. Okay? The mass and the spring constant are what are controlling the period. Let's hook a weight back on that, a mass back on that. Okay, never mind. So, 450 sample problem 12C. An auto spring problem. These are pretty common, and this is, in automotive engineering, this is one of the factors that goes into design for suspension systems. Because a suspension system's job is actually not to cushion your tush, it's to keep your tires in contact with the road. So bad suspension will give you bad tire wear because when you hit a bump, your tire will come off the ground and parts of your tire will actually not contact the road surface. In a moment when your tire is off the ground, you also have no steering control and you have no friction between the vehicle and the road surface because they're not in contact and friction is a contact force. So this is a big consideration in automotive design. How much does the vehicle weigh? What's the average mass of its occupants or cargo going to be? And therefore, how stiff do the springs need to be? So here, we're told that we have a 1,275 kilogram car. It's supported by 4 springs, which is typical. And we've got 2 people riding in the car with a combined mass of 153 kilograms. It goes over a pothole in the road, and the frame vibrates with a period of 0.840 seconds. For the first few seconds, vibration approximates simple harmonic motion. Find the spring constant of a single spring. So let me ask you this question. Why does it only approximate simple harmonic for the first few seconds?
After that, when it starts to slow down, it would be damping it.
Damping it with what? What's dampening it? Friction from what? What system in the vehicle is designed to dampen the oscillation? Shock absorbers. Yeah, the shock absorbers dampen that. Okay, so we know that T equals 2 pi square root of mass over K. We are solving for K. Now, we're looking at a single spring. So what fraction of that mass is the single spring out of 4 supporting? 1/4. So mass, the mass here is actually going to be total mass divided by 4. And that's a good place to start off with. So 1275 plus 153 kilograms, all divided by 4, gives us a mass per spring of 357 kilograms. And we were given T, we'll shrink that down to nothing, T was 0.84 seconds. 840 seconds, so we have 3 sig figs. Okay, so solving for K, we have T divided by 2 pi, quantity squared equals M over K. Opportunities for algebraic nonsense abound. Remember, if you're solving for something here, if you need to take the long way, do it. And multiply by K, so that would be K equals quantity T over 2 pi squared equals M. Then you can divide both sides by this entire thing. Solving for things in the denominator is the single most common place for folks to screw up. So we plug in our numbers. K equals 357 kilograms divided by 0.840 seconds over 2 pi quantity squared. Let's get a raw value for K. And this is another one where order of operations is going to be a booger. That's a record. Okay, so FIP tomorrow, 12A through C, plus concepts. Can't spell. Okay, that's it.